Hi everybody and welcome back to the second part of videos for trigonometry. So in the last set of videos you've seen already some trigonometric identities like the even-odd identity and the formula said that sine squared plus cosine squared is always equal to 1. And in this set of videos we're going to continue and cover a wide range of formulas that give you even more relations between trigonometric identities. So first thing up is a formula that's very similar to the even-odd set of formulas that we saw, and that is described here on slide as reflection across the y-axis. So what this set of formula does is it gives you a relation between cosine or sine of an angle and cosine and sine of pi minus that angle. And to see a little bit how these formulas come about, let's go back to our unit circle. Let's take a point P on there, defined by an angle theta. And now, as the title of the slide suggests, let's reflect that point across the y-axis. So we take the entire unit circle and we flip it 180 degrees across the y-axis. And what that does is it takes the point P into the point Q that I'm drawing here, and the radius becomes this. And if you look at this for a little bit, you'll see, and this is not so difficult, that as far as the coordinates of Q go, this point has coordinates minus x, y. And angle-wise, this angle right here is nothing but pi minus theta. And to see a little bit why that is exactly pi minus theta, let's choose a different color. You can derive that from the fact that this angle and this angle right here, they're the same. They're both theta. And the entire angle spanned by the x-axis, that's pi, so what's left here, that's pi minus theta. So that's our picture, and now let's write down what that picture tells us. If we look at the point P on the one hand, we have that the coordinates are x equal to cosine theta and y equal to sine theta. And now if we look at the point Q, we have that the coordinates are minus x and y, and these are also equal to cosine pi minus theta and sine pi minus theta. And if I put these two together, what I get is that cosine pi minus theta is equal to minus x is equal to minus cosine theta, and sine pi minus x is y is sine theta. And that gives us precisely the formulas that are up here. Now, up next is a set of 3 times 3 formulas known collectively as the shift formulas. And they're known like that because in each case what they basically tell you is if you take cosine or sine for an angle theta and then you increase theta by pi over 2, so you shift it by a certain amount, what do you get in return? And the first set of formulas, they're concerned with shift by pi. And you can see that in the expressions that are already on the slide, there's a pi, and we're shifting by pi. And if you look at the formulas a little bit in detail, what they basically tell you is if you take an angle, you increase it by pi, and you compute the cosine or the sine or the tan or whatever, what does that tell you in function of cosine of theta, sine of theta, and tangent of theta? And what you see is that shifting by pi almost gives you back the same trigonometric function, but the sign changes for cosine and sine. So you know, just as a side, that if you add 2 pi to an angle, cosine and sine stay the same. So cosine theta plus 2 pi is cosine theta, and so on. But if you add just pi, then you have to pay price of this extra minus sign. So we're not going to derive most of these formulas. I just want to give you a brief intuition as to where they come from. So if we take, again, our point P with coordinates x and y and angle theta. Now, if I take my angle and I add pi to that, I end up basically in the opposite quadrant. And I have this point right here, which again I'm going to call Q. So this angle here is pi, and this complete angle is pi plus theta. Now, if you look at what the coordinates of Q are, you'll see that the coordinates are minus x, minus y. And in effect, what we're doing here is we're reflecting not across the x or the y-axis, but we're reflecting across the origin. So we're basically taking for each point the point on the other side of the unit circle relative to the origin. And that's what gives us this minus x and minus y. And then maybe really quickly, if we again compare what both points tell us, we have that coordinates of P are x is cosine theta and y is sine theta. And for Q, now we have minus x is cosine pi plus theta, and minus y is sine pi plus theta. If you put 2 and 2 together, you get that cosine pi plus theta is minus x is minus cosine theta, and likewise sine pi plus theta is minus y is minus sine theta. So that gives us formula 1 and formula 2 here. And then formula 3 you basically get by dividing sine by cosine. At this point you can probably also see that there's other ways to do it. I encourage you to play a little bit with these formulas. The derivation that I'm showing may not be the most easy one, or it may not be the only one. So then next up, another shift formula. So now we're going to shift by pi over 2. So again, you can see here we have pi over 2, pi over 2, and pi over 2. And now we see something interesting happen. So we basically have that sine turns into cosine, and cosine turns into minus sine. So they basically flip over like this, if that makes sense. This set of formulas we're not going to derive, so they can be derived from the addition / subtraction formulas that we will cover later. So I will also leave the unit circle blank here. And then the last set is very similar, except that, again, we're doing something with pi over 2, but now instead of taking plus the angle, we have a minus sign here. And what you see is that the shift formulas are very similar to the original set, but you don't have to account for the minus and the plus. So maybe just to compare, what did we have before? When we had plus, then this was still cosine, but we had plus here that turned into minus sign. So here you have to be careful that you get the signs right. So these formulas as well, they follow from the addition, subtraction formulas. And I would say in terms of what are the really, really important formulas, these ones are very, very important, and you'll see them come up a vast number of times. So even though they appear as just 3 out of many, pay particular attention to these guys. So these formulas you can actually derive from the previous set that we've seen, but I will skip that. So here too, I'm not going to fill in the trigonometric identities. If you wanted to derive these from first principles, what you could do is, if you have your angle theta here, then this angle is pi over 2 minus theta, and then you can do something with the bisector to figure out where the other points lie. So I'm going to put the derivation of the formulas aside, and let's maybe quickly look at a couple of examples just to see how this works. So for the first example, let's compute the cosine of 5 pi over 4. So this is already not a simple value that we've seen in our table before, but what we can do is we can write this as cosine of pi plus pi divided by 4. And now this is good news because we know something about pi over 4, and we can apply our reflection across the y-axis formula to write this as cosine pi over 4. So reflection across y. And this is great because, as I said, we know what cosine of pi over 4 is. That's negative square root of 2 divided by 2. Let's do another example, and I'll put it on the right-hand side here. So as a second example, let's have a look at the tangent of minus 5 pi divided by 6. And here we can use several rules in the same problem. So first, we'll use the even-odd rule to write this as minus the tan of 5 pi over 6. So okay, that's a positive number inside the brackets here, that's good, we like that, but 5 pi over 6 is still not a number that we can deal with quite easily. But what we can do now is we can observe that, well, 5 pi over 6, that's pi minus pi over 6. And that's again good news because, hey, I have a formula for tan of pi minus an angle. I know what the tan and sin and the cos of pi over 6 are, so I think I can solve this. So here now I can use my formula and I'll write this as tan of minus pi over 6. So here I used, what I actually ended up using is the shift formula, the one that said that tan pi plus theta is equal to tan theta. And now, okay, I have again the tan of a negative number, so what I can do is I can take that minus sign outside and write this as tan over pi over 6. So let's another application of the even-odd formula. Now I'm almost done. I can look back at my table or know by heart that this is square root of 3 divided by 3, because that was one of those special values. There's another way of solving this. As I said, there are many ways of solving these problems, and no way is the best way. Depends a bit on what formulas you feel most comfortable with. But what you can also do, alternatively, is you can, let's see, where do we start from? So if we have the first step and we replicate that, then we can write this as minus tan of pi over 2 plus pi over 3. It's a different decomposition, but it's a good one because now we have that pi over 2 and we know how to shift by pi over 2. And then we can write this as cotan of pi over 3. So this is one of the shift formulas, and this should give you the same result of square root of 3